The goal of this video is just for you to have another example to look at. So you can always just try the example first on your own and then watch the video to see if you did your work correctly and send a question to your instructors if things did not match up. Alright, so for this example, we're looking at in 2012, it was found that 83.2% of Kentucky children aged 0 to 10 had received all the vaccinations for the DTaP. Vaccination rates are strongly related to insurance rates, so we wanted to see if this number had changed since the full implementation of the Affordable Care Act. So we sampled 1,395 Kentucky children in 2014 and followed them through 2016. Alright, so first, just kind of write down some numbers that I know. When I see this 83.2%, that was sort of a known number back in 2012, so it seems like a population proportion, or a P. So I'm going to say that my P is 0.832. It then said that we sampled 1,395 children, so I know what my sample size is going to be. And then finally, this changed part, even though it's not a number, is very important for me. When I already see that, I already know what my alternative hypothesis is going to be. Because of that changed aspect, it's going to tell me that that not equal to is going to be showing up. More specifically, it's not going to be equal to what it was before, or that 0.832 that I have at the beginning. Not stuff you have to do before you dive into the problem, but sometimes can be helpful. It then says from our sample we got the results found on the right here in our pie chart. We're going to interpret that plot in the context of the problem. So of course, first, just looking at my pie chart, I can see there's a much larger red group than blue. More specifically, the red is the yes, which is about 86% of my data. And then the blue is the no, much smaller, about 14% of my data. So how I could interpret this is of our 1,395 Kentucky children sampled, we found that 86.09% had received all the DTaP vaccinations. While the rest, or 13.91%, had not. Okay, so first, just sort of comparing. So it was 83.2%. That was of everybody in 2012. From our sample of almost 1,400, a little bit more than 86%. So I can see that that number is bigger, but again, it's just based upon almost 1,400 children, not everybody. So I've got to do a hypothesis test to really see, is this number different from that one or not? So we're going to use that data now to formally test the appropriate hypotheses using a 1% significance level. And we're going to go through and show all steps, including the conditions here. Please note, as you're working this problem, there is more room on the next page, so you don't feel like you have to try to fit the whole thing here. So this new number given to me is going to be my alpha of that 1%. All right, so my first step is to go through and do my hypotheses. And if I've already done what I did above, this is going to be pretty easy. I already have my alternative hypothesis written out because we just want to see if it has changed. So it could have gone up, it could have gone down. The null hypothesis is always the same symbol, the same number, and always an equal sign between it. Right, for our second step, it is just that decision rule. So I'm going to reject the null, and I like to say and believe the alternative if my p-value is less than my significance level, which here is at 1% or 0.01. Step 3, I am going to go ahead and do conditions here. So our conditions that we need a relatively random and unbiased sample. So we're looking at Kentucky children. We sampled Kentucky children. It doesn't really tell us exactly how we got these 1,395 children, but at least from what I know, I don't have any known bias here. Then I need to check that my n times p0 is at least 10. Now my n I already have labeled. My p0, so this 0 just matches up to this one to tell me kind of what number to use, so it's going to be that 0.832. So we're going to take our 1,395 times that 0.832, and we get 1,160.64. And we're just checking that that number is at least 10. And then my n times 1 minus p0, or 1,395 times 1 minus our 0.832, which will give us 234.36, which is also at least 10. Our other part of step 3 is our test statistic. So if I look at my formula for that, off of my formula sheet, of course you never need to have this memorized, will look like this. So we already have a couple of these because of what I did down here. We have our n, we have our p0. So I have all of those. The last thing I just need here is p hat. Now remember, p hat is the sample proportion. So here it's going to be the proportion of Kentucky children sampled that had received all the DTaP vaccinations. So in a sense, I want all of my yeses from my sample here. So if I wanted to, I can calculate p hat by taking this 1,201 yeses out of the 1,395. Or technically, it's really just this 86.09 as a decimal. But either way, you'll get the same number for that. So then plugging our numbers in here. So we have all those numbers, showing a little bit of some in-between math here. Our z should turn out to be 2.89. Now I'm going to go ahead and go to the next page so that I don't try to squish things here. As I go to the next page, the next things I'm going to need, I'm still going to need that z I just calculated. And then I'm going to need this alternative hypothesis sign. So getting there for step 4. So I'm going to first start by drawing my picture here. So our z is always centered at 0. Put my sort of little increments on here for myself. Our z that we just calculated was this 2.89, so I'm going to put that on my picture. And then this is when I have to figure out if it's a one-tailed or a two-tailed test. So that's why I need that alternative hypothesis sign, because due to that not equal to, it's going to tell me it's a two-tailed test. So what that means is not only do I want everything above positive 2.89, I also want everything below negative 2.89. Because we don't care that that 2.89 was positive, we just care that we were 2.89 standard deviations away from the mean. So this is when we do our p-value. You can do it two different ways. you can realize that these two areas are going to be equal to each other. So if I just find one of them and double it, I'm going to get the answer. So I'll do it that way here first. So I can just then take 2 times whatever I get when I look up negative 2.89 in my z table. You should feel very comfortable in reading your z table now. So you should find the 0.0019 in there when you look up the negative 2.89. So if I take double that, we're going to get 0.0038. The other way to do it is just to find the two separate pieces, and then you can add them together. So if I sort of pretend that this part isn't here and just focus on this piece, it's shaded left, so I can go straight to the table to look up that piece. And so for that piece, just as what I did above, we'll get 0.0019. Let me make that a little bit more legible here. Now for this other piece over here, since it's shaded to the right, I have to do that 1 minus rule for that piece. So I'm going to go to the table and look up that positive 2.89, and I'll find 0.9981, which then just gives me 0.0019 plus 0.0019 to give us that p-value of 0.0038. So both ways you get the same p-value. The first way is probably just a little bit quicker to get it. Alright, now either way that you did it, same p-value, we're going back to step 2 and checking, is our p-value less than 0.01? If our answer is yes, we are going to reject the null and believe the alternative. If not, we will fail to reject the null hypothesis and not believe the alternative. Ours here is less than 0.01. So we will reject the null hypothesis and believe the alternative hypothesis. So let's go through and write out step 5 to see why I'm actually going to add a little something extra here as well. So we're going to start with our alpha level of 0.01. Since we rejected the null hypothesis, there is statistically significant evidence. To support that. Now this is where our goal is important. So we do believe that the vaccination rate has changed. Since that 2002 value. But hopefully you can see that if I left it like this, it's not horribly useful. Yep, it's changed. It's sort of the obvious follow-up question, well, how did it change? Did it go up or did it go down? That's something I would definitely like to know, and I get that for free here. Like, I don't have to do any really more work. I can sort of see pretty easily what my answer is going to be. I can see this in a couple of different places. So first, I can see that this is what it was in 2012. Here's what I got in 2016. That number is higher, so I'm going to be able to say that that rate has actually increased. The other place I'm seeing that is in my z. This is finally where we do care about the sign of our test statistic. The fact that our z is positive is telling us that we are above or to the right of the mean. So that means that it's also gone up since the z was positive. So I'm going to say not only has it changed since 2012, in fact it has increased. So, and in fact has increased. Now, why can I say that? Again, my z was a positive value. Is telling me that. All right, next we just want to talk about why would a 1% significance level have been chosen here. So we generally use a very small significance level when a type 1 error is of great concern. So why would a type 1 error be a great concern here? So what would it mean for us to do a type 1 error? Well, here in context, that would mean that we believe that the vaccination rate has changed, because we would reject the null, so we're going to believe that it has changed. The error, it really hasn't. Now, why would that be a very big deal here? Well, we're looking at the Affordable Care Act, and if you don't know much about it, people had pretty strong opinions about if it was a good thing or a bad thing. So if I believe the vaccination rate has changed, I'm either going to think that the Affordable Care Act is doing a great job because the vaccination rate has increased, and so our children are becoming immune, hopefully, to more of the different diseases out there. Or it could have also changed in the negative direction. So those people that are very much against the Affordable Care Act might just say, you know, see how it's not working. I told you it wasn't going to work. Things are getting worse. Right? So I'm going to cause some concerns between people about these very polarized visions that they have about the Affordable Care Act. So the reason why would this be a big deal is really because of the political backlash of it. Is because if people start either saying what a great job it's doing when it really isn't, or start saying it's doing a horrible job when it really isn't, I wouldn't want to see something like that happen. Alright, finally, we're just going to verify how to get this p-value in StatCrunch. So if you just pulled up your StatCrunch page here, and I'm just going to open a blank worksheet. I don't need a data set for this one. We're just going to be going to Stat, Proportions, One Sample with Summary. So the numbers I need to give it here are my two numbers that created p hat. So there was 1,395 total observations. 1,201 were successes. Now, where am I getting that number? That was our number of yeses. Those were our two numbers here that I used to create that p hat. Then I just need to make my hypotheses match what they look like in step 1. So my number here is 0.832. Notice how it automatically changes down here for us. I could change this sign if I needed to, but ours is a not equal to, so I can leave that as is. And then I hit compute, and we'll see many of the numbers that we used here. So here's that 0.8609 that we used for our value of p hat. This 0.01 number makes me realize where I have a typo, or technically a righto, right here. So make sure I go ahead and change that. That was me forgetting to get rid of a couple of those zeros here. So that should have just been 0.0100 for that number. But my 0 is in the wrong place. I apologize for that. Because you'll see that, oops, 0.0110 number right there. And then finally, there's our z of that 2.89 and our p-value of 0.0038. So those were our numbers that we did get here as well. So there's our 0.0038. Alright, so hopefully we got the numbers to match besides my little right-o that I had there for you. But at least the z was correct from there.